All right, so this video here, here's our guiding document. We've done homework 3.1, note 17. We did a little bit of 3.2, just the first couple problems here. But then the questions start asking us about things like energy. And that's where we're going to need to do notes 18, electromagnetic waves. So here's our notes. Let's get our title going. Magnetic, it's getting squishy. Waves, we'll write really tiny so it fits, maybe. That was close. Okay, write tiny. Electromagnetic waves. Now, specifically for this notes, there's a couple of different pictures that we're going to need to cut out. We're going to cut out this picture. You can cut them out separately if you want. We're going to need this one and this one below it. So here are the pictures that you'll want. Notice all of these cutouts aren't really in a particular order. They're just kind of in there based on what fit on the page best. So pause this video and cut out 1, 2, 3, 4, these 4 pictures. All right, once you've got everything cut out here, the way we're going to position this on the page, we're actually going to start with this one here, right up at the top. So just as a reference, we're not actually necessarily using this, but a transverse wave is just one that goes up and down. Specifically, the way electromagnetic waves work is one way we have an electric field, and the other way is a magnetic field. So I'm going to do my best here to kind of show what's going on between the two. Let's pick some random colors. We'll do pink for the electric field. And think of, let's see, this is kind of going up and down, up and down, up and down. So there's the electric wave, up, down, up, down, up. And then we've kind of got a forward, backward. So instead of an up, down, forward, backwards motion on the magnetic. So I'll do that one in. Let's do green for the magnetic. Doesn't really matter. I just picked some random colors. So instead of up and down, this is like a push-pull forward towards us, back away from us, towards us. Oops, did not follow that line very good. Oops. And away from us. So here's kind of what I'm getting at. See how the waves, one is going up and down, and the other is going back and forth. This is what we're referring to when we look at this picture here. Up and down, and back and forth. So here's another fantastic example. We've got the mechanical wave on top that's just moving up and down. That's like a general wave. But when we're dealing with a light wave, an EM wave, sometimes B, see how the side says B? B is magnetism. So we've got the same motion, except for one is the general wave and one is the light wave traveling at the speed of light. So just letting this sit here for a minute so you can see it clearly without my hands kind of wobbling it. We're not really going to separate out the electric from the magnetic component. We're going to kind of think of it as just one big wave, but it is important that you see like visually the distinction here. All right, so there's our first part. If you want, you can kind of shade this in or don't, whatever. But we've got our electric field, and I forgot to label the magnetic field. Wow, that's super blurry, my bad. There you go, electric, magnetic. So, for definitions here, we're going to say electromagnetic waves, or EM waves, are caused by vibrating charges because a moving charge produces both an electric field and a magnetic field. All electromagnetic waves are forms of light. I'm going to do that in all caps because it's very, very, very important. Underneath that, we'll stick this picture. It's the same one that we tried to draw in the last set of notes. I'll flip back to our attempt here. We tried the really long waves and then getting shorter and shorter and shorter. But this one just has it a little bit more fleshed out. We've got the long wave over here, whoop, longer wave, and then it gets shorter and shorter and shorter and shorter and shorter and shorter wavelengths as we go to this side. Visible light is this little teeny area right here where we can see the colors, red, orange. You don't have to color this if you don't want to, but I like coloring, so I'm gonna do it. Red, orange, yellow, green, bluish, dark bluish, and purple. Now double checking myself before I double wreck myself. Is my rainbow going the correct direction? The answer is yes, because infrared below red is here on the red side, and ultraviolet is extra towards the violet side. So my rainbow is correct. all of this stuff in here, all of this, all of this, all of this, all the way including IR, whole thing, all the way up to there, but I don't really want to go that far. Humans cannot see this, and also this. Humans can't see over there. Humans can't see over here. We can only see, I'm going to draw a little eyeball, from here to there. This very teeny region. Specifically, the area that we are able to see, let me just write this off to the side. Human visible light is from 400 nanometers-ish to about 700 nanometers. The 400 side, I should have maybe done this reverse, but the 400 side is the purple, and the 700 side is the red. And that kind of makes sense, because if this is the wavelength, red is a longer wave. It's going to take 700 steps versus the 400. So that's where these two are going to come in. So underneath the 400, this is backwards from our picture, but it's totally fine because there's no proper way to orient. There's no proper way to orient these. Just make sure you know that purple has the short wavelength. It's 400. Let's see, how am I going to tape this? Just like that. When I look at a purple wavelength from here, crest to crest, I would only be able to count 400 little spaces between there. With red, if I were to actually do this, with red, I would be able to count like way more. I should be able to count 700 versus 400. So purple has a high frequency. It's passing by much more frequently, and it has a shorter wavelength. Low frequency, long wavelength. Now, one thing that's important about what I wrote here is I wrote human visible light because our eyes are different, and I don't want to like pretend that humans are like super great or anything. But other animals, other creatures have different eyes, and they can see maybe their little area is more into the ultraviolet, or maybe theirs is more into the infrared. Or sadly, you know what's really sad is that dogs can only, like, if we can see this much of the rainbow, take out purple, take out red and orange, and also the darkest of blues. This yellow, green, and blue is all that your dog can see. So I've got some really sad pictures here of what the difference, let me actually zoom in so it won't be so wiggly. Here are the here's the what humans can see, and dogs don't really have that same spectrum. Like I said, it's just the greenish, the yellowish, and the bluish, and so they're not going to be able to see as much as we do. And this is actually really sad because, like, we buy them all these colorful toys and balls and like red, orange, yellow, we've got the whole rainbow here, but then kind of what they see is just yellow, 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 blue, green. Now another really cool animal here is a bumblebee. And so a human vision is what we're used to. We can see, like I said, from 400 to, I should make this tinier. Doop, there we go. 400 nanometers, which is the purple side, to about 700. And past that, it goes into infrared on this side. And over here would be ultraviolet. So now bumblebees, they're losing a lot of their red color. They can't quite see that as good, but they can see into ultraviolet past where we can see. So they can go all the way to like 300 nanometers. Now the reason why this is significant is, check this out. So this is a picture of a yellow flower for us, like yellow with bright sunshine on it. And it just looks yellow, 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 yellow. But to a bumblebee who can see, bumblebees can see more into that UV region. When they see flowers, it kind of has the markings on it of like where to land. Like, hey, the pollen, the stuff you need, it's in here. Check it out. And so it looks more like a target that they can, they'll know where to land. So that's pretty cool. Like what we consider to be like visible light is not necessarily the same as what other animals and creatures do. So subsequently, like military, they use infrared goggles that rely on picking up the body heat instead of actual visible light from your eyes. All right, so next on our little section here, we're going to talk about energy. I usually do everything to do with energy in orange. I'm not really finding my orange marker, so I'm going to use yellow. I don't like it so much, but it is what it is. So we'll go with this golden color for energy. As long as it shows up on the projector, I'm fine with it. It seems like it'll be okay. When you look at these two waves, the purple versus the red, like not as good. Okay, hold on. Purple, and then red is like a lot less. This one is obviously the more energetic wave. Purple is a higher energy color than red. So over here, high frequency, short wavelength, and we're going to put high energy on this side. Low frequency is going to correspond to a low energy wave. There is a direct relationship between frequency, let's see, don't want that color, frequency and energy. If the frequency is really high, then the energy is going to be really high. They run together. They're directly related. If the energy is low, it must not be undulating very frequently. So, looking at the bottom of the page here, you should still have maybe a couple fingers worth of space. We're going to do a new equation to figure out how to calculate energy calculations. We're going to finish this up here in a second. But, let's see. We need a couple of colors back. I'm going to use blue for the wavelength, like I always do. I'm going to use red for the frequency, just like on the previous page, we color-coded wavelength and frequency. So I'm using these colors. And now, since I can't really find my orange marker, we're using yellow for energy. One way that we can calculate energy is using the wavelength, and the other uses the frequency. So let's make a little T table, like a little chart. There's two different ways to do it, so I want to have both of them and compare. Over here, let's put the energy calculation that's using wavelength. And over here we'll do the formula for the energy calculation using frequency, that dabbing letter V. Energy is measured in units called joules. Not like a gemstone kind of jewel, not that kind. And also not the vaping jewels. Joules, again, whatever. It's Joule, joules. Abbreviation is letter J. So using frequency, let's start with this one because it's a little bit easier. To calculate the energy, energy equals the energy is measured in J, letter J there for joules. Energy equals this thing called H, letter H. We don't know what that is yet. I'll just write it. H times the frequency. Remember that the frequency is measured in inverse seconds. And H is new. H is going to be a new thing. Last time we talked about C, letter C, and that C is the speed of light, and we always plug in 2.998 times 10 to the 8th power for C. H is really similar. It's also a constant, and every time in this unit that you see the letter H, you're going to always plug in this number here. 6.626 times 10 to the negative 34. Always plug in this number for h. It is called Planck's constant. And with, whoops, why did I just write important? It is important, but I meant to write constant. Planck's constant. It is important that we have this value in here, even if you don't 100% understand like why it's necessary, that's okay. We need to plug this in order for our units to cancel. I'm not super stressed about how our units cancel right now. We're just writing the formulas. So if the problem gives you frequency and says the frequency is blah, 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 calculate the energy, this is what you're going to plug in. The other calculation is going to be energy equals lots of color coding in this chapter. This one is going to be energy equals H, same exact H, times the speed of light, letter C, divided by the wavelength. So when you run this problem, for C, which is the speed of light, the previous page said whenever you see letter C, plug in 2.998 times 10 to the 8 meters per second. Letter H, this is our new one. This one's always going to be 6.626 times 10 to the negative 34. And the wavelength, we plug in meters. So if the problem gives you nanometers, you'll need to convert nanometers into meters before using this equation. And let me label that this is energy measured in joules. So when a problem says calculate the energy, you have two choices. You can use the first equation, you can use the second equation, and mostly whichever one you choose depends on your personal preference. Like when we do the homework problems, I'll give you examples of which equation I would choose and why. But like right here, not going to do it right now, but here's an example. Determine the energy associated with a wavelength of 418 nanometers. So for this problem, I'm for sure going to want to do the energy calculation using wavelength because it specifically is giving me the wavelength. On a different problem, if it says, if this one gives me the frequency, number 8, it says blue light has a frequency of this. Cool. Now I can use the frequency formula to calculate the energy. The only thing that sometimes trips up students here is that down here on this wavelength, if it's in nanometers, you can't use it. Wavelength cannot be in nanometers. You must convert it to meters first. And when we do the homework, I'll provide you some examples with that. So here are the two equations for how we measure energy. And when we measure it, we're going to say, this has this much energy in joules.